Camille. Good morning, everyone. Thank you for being here. Thank you for watching online and for following the symposium remotely. And my name is Ricardo Nascimento. I am a PhD student at Loughborough University. And I'm glad to present our paper, Craft Sensations and Exploration of Digital Fabrication Methods Applied to Inflatables for Embodied Interaction. This paper is a result of a collaboration between myself, Ricardo Nascimento, Saskia Helinska, and Anastasia Pistofidou. The study was carried out at IAC, Institute of Advanced Architecture in Barcelona, Spain, and is part of my PhD research at Loughborough University and also part of Saskia research at Fabricademy, which Anastasia is one of the founders. So this presentation is divided into 4 parts. In the first part, I explain our motivation for this study and why we think it's relevant. Next, I detail the theoretical underpinning, methods, and applied techniques. Following this, I briefly share the design process of the actuators and how we evaluated them. And finally, I share our findings and conclusion. If you want a more detailed explanation, you can read the paper online, as Camille said. So first, the context. Recently, we have witnessed the proliferation of smart objects in almost every context of everyday life. Those objects, embedded with computational power, can sense the body, the environment, and digital data and react according to programmable logic. Living in the technologically mediated world, we interact with these objects the same way we interact with anything else. That is, through our body, or to be more specific, through our senses. As smart objects can have different shapes and materials, such as a phone, a piece of clothing, or even a table, the ways in which we interact with the user may vary. They are everywhere, and here I quote Weiser, and they weave themselves into the fabric of everyday life until they are indistinguishable from it. This is his quote. The consequence is that those technologies, through the interaction with the user, invite some actions while inhibiting others. As a result, we engrave the understanding of ourselves on them, and in turn, they shape us. This is clear when we look at the smartphone and how it has changed how we meet, socialize, play, move, and use our bodies. And that is why it is relevant to research how to better leverage the body's capabilities when designing interaction, especially for interaction through on-body technologies such as wearables and prosthetics. In addition, designer, artists, developers, and education can apply our analysis to product development, artistic expression, performance, installations, and educational contexts. So one of the ways to couple a user action and a system response is through embodied interaction. This area of research is based on the existential phenomenological approach after Merleau-Ponty that claimed that our subjectivity is embodied. This embodied self is the foundation of any possible lived experience, blending the mind and the body and recognize the epistemological value of the body. We also took inspiration from the somaesthetic approach, which combines philosophical theory, which is heavily inspired by phenomenology, with practical activities for the emulative study of the experience and the amelioration of perception. Richard Schusterman, its founder, claims that when we perceive better, we might better understand ourselves and be empathetic with the experience of others. And this paper also aligns with the approach of soma design. It builds on technological affordance to design somaesthetic experience. In our case, the technology is tied to inflatables that we use to construct soft robotic actuators for embodied interaction. We have explored 2 techniques that are easily executed in a makerspace environment, our context, for this study. Silicon mold, illustrated in the left picture, and heat sealing technique displayed on the right image. I have here with myself, and then you can check later if you want, like some results, like this is the result of the heat sealing technique. And I have also how we applied the inflatable to textile material. So if you want to experience the sensations afterwards, just talk to me. And I'm glad to share this with you. Okay. But before I explain those techniques, I want to share how we decide on the sensations we chose to explore, which is poking and grabbing, and our somaesthetic inspired method to ideate and evaluate those sensations. The first method we used was the observation of non-verbal social interactions. For that, we observed people in a cafe near Ayak, and we noticed that poking and grabbing were often using strategies to get someone's attention. After that, we did a literature review of projects exploring those gestures. We found that other researchers analyzed them for notification purposes, but only for the finger, hand, and arms. So we instead developed an actuator to be placed in any body part. We also considered the social and ethical implications of such gestures. It is essential to clarify that we were interested in the sensations elicited by the gestures. Then the gesture might be considered aggressive or maybe undesirable, depending on who performs them, especially interactions between different genders and power statuses. Therefore, the sensations might be related to unsettled feelings depending on the context. When designing body interaction, ethical and social considerations are critical. Inspired by the body awareness promoted by the somaesthetic approach, we decide to proceed with these gestures that you see here in this picture, and we start to perform them in ourselves to pay attention on the quality of the sensations they provoke and how the hands move while performing those up here the video. Yes. So before this experimentation, Saskia had explored different geometries and materials for inflatable constructions. Here you see the result of this first exploration. So each iteration produced a different movement when the air was inserted. So we have like air pumping in and out of these constructions. We use visual comparative analysis between the inflatable and the hand movements to select the best geometry from this list to our purpose. Yes. We also developed a circuit board with the help of the technicians at the Fab Lab to control an air pump. You see in this picture on the left. And to test, we applied the actuators on ourselves and assess the sensations elicited by the actuators compared with the one elicited by the hand. Now I will share the process of the crafted the sensations. We start with the poking. So this poking sensation. We selected a circular geometry because it deforms upwards when actuated. Like it's sort of a bubble that goes up when you put air, creating pressure in one point, similar to the sensation of poking. We start with the heat sealing technique and using the silicone ball technique for comparison. The design process starts with the heating welding technique to be adapted from the work of Aeromorph in 2006 from MIT, where they used a heated nose of a 3D print to perform precise sealing, which is result in this thing here. So in this video, you see the 3D printing. Basically, you have to turn off the sound. It's just the sound of 3D printing. Basically, you just don't put PLA and use the nose as like a heated element that goes and perform the sealing very precisely. And so then on the screen you can see the print in action, and on the side, so we can come back to the presentation, there's an illustration that shows the material adaptation we found ideal. This is Saskia's previous research as well. So we have like a baking paper on the top. It's a very cheap material that allows the nose to really slide smoothly, which is great. And we also use a neoprene fabric layer to weave here this layer like that, to give some malleability to the composite. So we could apply more force in the plastic, and therefore the ceiling gets stronger and more robust without breaking it, without tearing the plastic apart. This is the result inflatable, and here is the geometry we chose. So as you can see, created these bubbles. When they actuate, will create pressure on the skin. So next, we experiment with silicone mold technique, and for this actuator, we built the molding using laser cut technique, which is like a piece of acrylics that you cut and separate, then you glue together to make this mold. After the mold was assembled, it was time to use the silicone. The silicone comes in two parts that should be mixed in equal volumes. After mixing for about 3 minutes, we use a vacuum chamber to eliminate the bubbles. After that, we carefully pour the silicone into the mold and let it rest in a level base for 4 hours. It depends on when you buy the silicone, you might want to check the data sheets to check the proper time for curation. After the silicone was cured, we took it out of the mold and glued it into a piece of textile. It is imperative to consider the type of textile used for the application. For example, and here's the illustration. If you use a stretchable textile, the deformation will go towards outside of the body. If you use a rigid text, and this is good, like for example, to create visualizations, like to create volumes going on your clothes. And however, if you choose a non-stretchable material, the deformation will happen inwards. So, and this is suitable for like haptic feedback, which was what we wanted to have. So, and then now the design process of the grabbing sensation. We decided to explore the silicone technique for the grabbing sensation, altering a popular open source soft robotic gripping design. And this was because the gripping movement is similar to the grabbing. So here you see this one. So if you are into like open source things and digital fabrication, you'll find this online. And so we got this geometry as inspirations. We took out 2 legs and made this version here. So we experienced the sensation in our wrists related to the poking sensation. The silicone performed better and provide better control. So we like better the silicone. However, heat sealing, which is this technique here, is suitable for low resource contexts. It's very cheap. You can change these materials, and even using like plastic bags from supermarkets if you want. It works pretty well. And also, even if you don't have a 3D printer, you can use like a heated element. You can use, for example, a soldering iron if you regulate the temperature very low, and you can create these geometries by hand. So if you are in a context that doesn't have much resources, this technique would be best. As for the grabbing, we arrive at the sensation that resembles a grabbing, however still very different from the one performed by a human hand. This might be because touch involves several mechanoreceptors working in sync and depends heavily on the context. Thus, it's paramount to design the conditions for the sensations to be perceived in a specific way intended by the designer. And this could be by acting on other sensory inputs like visual or sound, or combining different inputs to make it stronger or make it less stronger, your intention. So for future work, it's recommended to test actuator in other body parts, because even though we said that we wanted this to be put in any part of the body, we only test in the wrist, so it has to be testing other body parts, and also a longitudinal study to investigate the perception and impact of the sensations in real life context. Because lots of the research, like this one as well, we test in a controlled environment, and life is not a controlled environment, so it would be interesting to test this in other contexts. We hope our alternative method to ideate, construct, and test soft actuators from more subtle feedback help designers, developers, and artists in their creations. And just one last thing, we identified this can be applied for VR, rehabilitation, entertainment, educational. These are like a potential areas of use that we identified, but yet did not explore. So thank you very much.